Hello, bachcho, kaise ho sab? Welcome. Today we are going to tackle a very important topic from our Unit 14, Semiconductor Electronics, the PN junction. Now, I know the name sounds a bit complex, hai na? But don't you worry. By the end of this session, I promise you'll understand it perfectly. And most importantly, everything we discuss will be completely exam safe. So, chalo, let's get started.
So let me ask you a simple question. Think about your phone charger. We use it every single day, right? You just plug it in and it works. But have you ever wondered how it's so smart? It never sends the current in the wrong direction, which would completely fry your phone. So how does it know which way the current should flow? Well, believe it or not, the secret to that magic is exactly what we are going to study today. All right, so the story of a PN junction, it basically has two main characters. Think of it like a movie. We have two different types of semiconductors, and when we bring them together, something absolutely amazing happens. So, who are these two characters? Cello, let's meet them.
Okay, so on one side, we have what's called a P-type semiconductor. A simple way to remember this is P for positive. Why positive? Because it has an excess of holes. Now, what are holes? Just think of them as empty spots, places where an electron should be, but isn't. Take it? And on the other side, we have the N-type. You can probably guess, N for negative. This side has lots and lots of extra free electrons just roaming around. So to summarize, one side has many empty spaces, and the other side is crowded with extra occupant.
Here's a really simple analogy to help you remember this forever. Just imagine the N-type is like a super crowded market, like a Sunday bazaar, packed with people. These people are our electrons. And right next to this market is the P-type, which is like a very quiet, empty street with lots of empty parking spots. These empty spots, well, those are our holes. It's a very simple picture, but it helps a lot. Just keep it in your mind.
Right. So now, what do you think will happen if we suddenly open a gate between that crowded market and that empty street? It's obvious, isn't it? People from the market will naturally start moving into the empty street to find some space. Well, guess what? The exact same thing happens here with our semiconductors. And this very natural movement has a name in physics. It's called diffusion. It's a really fundamental process. You see it everywhere. It's simply the tendency of things to move from an area where there's a lot of them, a high concentration, to an area where there are very few of them, a low concentration. The best example? Just think of spraying a perfume in one corner of the room. After a few minutes, you can smell it everywhere, right? That's because the perfume particles have diffused throughout the room.
So let's apply this to our junction. Exactly as you'd expect, the extra electrons from the crowded N side, they see all those lovely empty spots on the P side, and they start to rush across the boundary to fill them up. And at the same time, because electrons are moving from N to P, it looks as if the holes are moving from the P side over to the N side. It's this huge difference in concentration that causes this initial rush across the border.
Now, think back to your basics. What do we call any movement of charge? Come on, you know this. It's an electric current, right? Exactly. So this initial migration, this great migration of charges across the junction, this is a current. And we give it a specific name, the diffusion current. Simple enough? TK? But, and this is a big but, this movement can't just go on forever. That would be too easy. Nature always tries to find a balance. So as these charges move across, they actually create a new situation, a situation that starts to push back and oppose the very movement that created it. It's really fascinating, actually. Let's see how this happens.
Okay, let's break this down step by step. Look here. When a free electron from the N side jumps over to the P side, what does it leave behind? It leaves behind its parent atom, which now has one less electron. So it becomes a positive ion. And this ion is fixed. It's stuck in the crystal. It cannot move. TK? Now, on the other side, when that electron fills a hole on the P side, the atom there gains an electron, so it becomes a fixed negative ion. So what's happening right at the junction? We get a layer of fixed positive ions on the N side and a layer of fixed negative ions on the P side. This region in the middle is now empty. It's depleted of any free charge carriers, and that's exactly what we call it, the depletion region. Now, what happens when you have a layer of positive charges next to a layer of negative charges? You get an electric field. It's like a tiny battery has formed right there at the junction. This electric field creates a potential difference, and we call this the barrier potential. And it does exactly what the name suggests. It acts like a barrier. Think of it like a big hill or a speed breaker on the road that makes it much harder for any more electrons from the N side to climb over and get to the P side. it slows down the diffusion. So because of this barrier, the diffusion current starts to slow down. But the story doesn't end there. In fact, this barrier itself creates a second type of current, one that flows in the opposite direction. And it's this second current that finally brings the whole system into a perfect, stable balance. This second process is called drift. Now, you have to remember, even though the p side has mostly holes, it still has a few free electrons, right? We call them minority carriers, and the n side has a few minority holes. Now, for these minority guys, that electric field at the barrier, it's not a barrier at all. It's actually a helping hand. It's like a slide that quickly sweeps them across the junction in the opposite direction. And this movement of minority carriers, well, that creates our second current, the drift current.
So picture this. When the junction is first formed, the diffusion current is very strong and the drift current is very weak. But as more and more charges cross over, the depletion region and the barrier potential grows stronger. This makes the diffusion current weaker, but it makes the drift current stronger. Eventually, a perfect balance is reached, a point where the diffusion current trying to go one way becomes exactly equal to the drift current being pushed the other way. This stable state is what we call equilibrium.
So here's the bottom line. In a p-n junction that's just sitting there with no battery connected, what we call an unbiased junction, the diffusion current is perfectly canceled out by the drift current. They are equal and opposite. And what's the result? The net current across the junction is zero. Nothing flows. Everything is in a perfect, stable balance. Okay, so now we understand how this amazing junction forms and finds its balance. But this brings up a very, very common question. A question about how we actually make one. And listen carefully, because this is what I call a silent killer concept. A small doubt that can really confuse your understanding if it's not cleared up right now. Many students think this, and it's a fair question. Sir, instead of all this complicated manufacturing, why can't we just take one block of p-type material and one block of n-type material and just stick them together? Maybe press them really, really hard. It seems logical, right? Well, the answer, and this comes directly from your NCERT textbook, is a big fat no. It's absolutely not possible. And here's why. Even the smoothest, most polished surface you can imagine, under a microscope, it's full of bumps and gaps. These gaps are huge compared to the distance between atoms, so you can never get that perfect continuous atom-to-atom contact that is needed for the junction to form properly. So please remember this for your exams. A p-n junction has to be fabricated from a single continuous crystal, not two pieces stuck together. So there you have it. We've seen how the junction is formed, the two currents, and the final equilibrium state. Now, let's just quickly wrap up everything we've learned and talk about why this one little thing is so incredibly important. All right, here's a quick summary for your notes. Just remember these 4 key points. First, a p-n junction is formed on a single semiconductor crystal. Second, 2 main processes are at play. Diffusion, which is because of the concentration difference, and drift, which is because of the electric field. Third, these 2 processes create the depletion region and the barrier potential. And finally, fourth, at equilibrium, the diffusion current equals the drift current, so there is no net flow of charge. That's the whole story in 4 points. And you might be thinking, okay, sir, but why does this matter so much? It matters because this simple p-n junction, it is the absolute heart, the fundamental building block of all modern electronics. The diode in your phone charger that we talked about, it's just a p-n junction. The millions of transistors inside your computer's processor, they are built using p-n junctions. Literally, everything depends on understanding this one concept. And that brings us to a final, really exciting thought. We've learned about this balanced barrier that stops the current. But, a balanced do-nothing state isn't very useful for building devices, is it? The real magic, the whole point of electronics, begins when we learn how to control this barrier. How can we apply an external voltage to make it smaller or bigger? How can we turn the flow of current on and off? How do we use this tiny barrier as a key to unlock the entire modern world of electronics? Well, that is exactly what we will explore in our next session on biasing the p-n junction.